This video lecture is meant to show you how we can find enthalpy from ways other than what Rosengarten presents to you. There's a total of 4 ways that we're going to explore on how you can find the energy of a reaction. And you already know some of them. One way is to look up the enthalpies on a reference table. You've already known how to use reference table I, and all you need to do is find the particular reaction you are interested in. And for example, let's say the forming carbon dioxide gas. And you can look at the enthalpy there. You can see that it's a negative enthalpy, which means, of course, that it's exothermic. Now, this particular reaction, because it is a formation reaction, all of these are synthesis reactions, otherwise known as formation. Okay. You can also find this enthalpy in another reference table B. This is AE reference table B and would be found at the back of your booklet. There is a column here that shows you enthalpies of formation. So to make 1 mole of these compounds from a synthesis reaction, it would take this much energy to do so. So for example, in reference table I, we saw the formation of carbon dioxide gas to be negative 393.5 kilojoules to make that 1 mole of carbon dioxide gas. Well, that information is essentially shown here to a different number of significant figures. So the formation of CO2 gas from its elements would release 393 kilojoules to make that 1 mole. I recognize there's a discrepancy in the significant figures and possibly the rounding, but essentially you can see that that information is the same. A second way that you already know how to find the enthalpies of a particular reaction is to interpret it from a potential energy diagram. You can see here we have 2 potential energy diagrams. We have one that is an endothermic and we have one that is an exothermic. Regardless, to find the delta H, the enthalpy, the change in the enthalpy, you needed to know the potential energy of the reactants and you needed to know the potential energy of the products, and you subtract those 2 numbers. So how do you find the delta H from a potential energy diagram? You would find the difference. You would subtract between the potential energy of the products and the potential energy of the reactants. But how can we write that as a math equation and ensure we're still going to end up with the correct positive or negative sign? Well, there's an equation to find enthalpy if you know the potential energy of the products and you subtract the potential energy of the reactants, and I'm going to use an abbreviation here, RXT, for reactants. And the delta H for the reaction, RXN, is reaction. Those are just silly little chemistry abbreviations. This will always, if you always start with the products and you subtract the reactants, you're always going to get the correct positive or negative sign. That will reflect your exo or endothermic reaction. Now don't fret, this equation can be found on reference table T. In the thermochemistry section, it is written like this. So the enthalpy of the reaction is equal to the delta H, the enthalpy or the potential energy of the products, minus the potential energy or the enthalpy of the reactants. Okay, so that equation is there for you to not have to memorize it. So that's pretty cool. So the third way of finding the enthalpy is really this equation. You've already been using it, but we haven't really written it down as a math equation, and we've only been using it when using graphs, looking at potential energy diagrams. So now we're going to use that equation, the enthalpy of the products minus the enthalpy of the reactants, but we're going to get our enthalpy information for all the chemicals in our reaction from the reference tables. So if we take a quick look again at AE reference table B, this is all data that is measured at standard conditions. and it doesn't really matter what those conditions are. I think it's 0 degrees Celsius and 1 atmosphere. But those are the kind of problems that we'll be working with anyway. Okay, so our first problem is going to be looking at this particular reaction right here. This is ammonia reacting with oxygen gas to form nitrogen dioxide and water. And we are going to look at this equation now, which looks a little bit more complicated. So the enthalpy of the reaction, that little degree sign is just to make you recognize that we're working at standard conditions, which is given. We're always going to be working in standard conditions, so you don't really need to worry about that too much. The sigma right here means you're going to have to sum up all the enthalpy of all the products, and we will subtract from that the sum of the enthalpy of all the reactants. Okay, so we're going to work through this first example, which is not on your handout. So you might want to write this down on a separate piece of paper so you can use it as your guide for the problem set today. So we're going to start by just writing the equation out before we substitute any numbers in. So the enthalpy delta H is equal to the sum of the enthalpy of all the products. And I'm going to use brackets here. You'll see why in a few minutes. And we are going to subtract from that the sum of the enthalpy of all the reactants. All right, so now we're going to start substituting numbers in. Delta H is equal to, all right, we got to take a look at our products. We have two products. We have NO2 in the gas form, and we have H2O in the gas form. Our reactants are NH3 in the gas form, and I'm going to erase those because I realize I've obliterated the coefficients. We're going to need those. So we're going to go to the reference tables, and we are going to look up the enthalpies of all these compounds. Remember, enthalpies of elements have 0 enthalpy, right? It doesn't take any energy to form them because they already exist. This is how they naturally exist in the world. So they all elements are just considered to have a 0 enthalpy. So let's take a look at that reference table. And here I have circled the compounds that we need the enthalpies. And if you're wondering about this free energy column, we'll get to that later this unit. Right now we're focusing on the enthalpies of formation. Notice that the unit is kilojoules per mole. That's going to be important. Okay, so take note of those as we go back and look at the problem. Okay, so our first product is 4 moles of NO2. So I'm going to keep my products inside of a bracket, and I'm going to recognize that I have 4 moles of NO2, and I am going to multiply that by positive 33 kilojoules per mole. That was the information that I found in the reference table. And to that, I'm going to add the enthalpy of the water in the gas form. I have 6 moles of water. That's just coming from the coefficients, the 6 right there. Now be careful that you looked up the enthalpy of water in the gas form, because there is an enthalpy for water in the liquid form, and it's a simple mistake to make, but the one we want here is negative 242 kilojoules per mole. Okay, so everything in those brackets right there represents the sum of the enthalpy of the products. Now we're going to work on the reactants. So I'm going to subtract and then open up another bracket for my reactants. I have 4 moles of ammonia, so I'm going to recognize that I have 4 moles of ammonia. The enthalpy for the formation of ammonia is negative 46 kilojoules per mole. And the enthalpy of the oxygen is just 0, so I'm just going to add 0, and obviously that ends our sum of our reactants. So now it's just a matter of just kind of keeping track of the products, when you multiply these numbers and the signs on the numbers. So I'm going to be sort of deliberate as I work through this problem. First of all of these moles are going to cancel, so your unit is going to end up being in kilojoules. Slick. All right. 4 times 33 ends up being 132 kilojoules. Okay, that is a positive number. To that, I'm going to add 6 times negative 242 is negative 1,452 kilojoules. And I'm going to keep that in parentheses only because I want to make sure that I honor the fact that there's a negative sign there. Okay. I'm going to continue to simplify. On my reactants, 4 times 46 is negative 184 kilojoules. Okay. All right. Now, we've got to start recognizing what we're doing with these negative signs. Subtracting a negative is going to end up being addition. Adding a negative sign is going to be subtraction. So let's simplify. Continue to simplify. 132 minus 1,452 is negative 1,320. Because this is subtraction, I want to maintain my significant figures to the ones place, so I'm going to put a dot there, a decimal there, and that's kilojoules. Okay. Now my reactants, I'm going to add that 184 kilojoules, and finally I can get to the simplification of adding those two numbers together, in which case you get negative 1,136 kilojoules. So this is an exothermic reaction, and if you were to go back up and report this, I'm going to erase that so we can do this a little more cleanly. The delta H for this reaction is negative 1,136 kilojoules. All right, the remaining problems in your handout will be in your handout, and so I'm not going to show those here. I'm going to let you take the opportunity for the rest of this time in the class to work on these 1, 2, 3, 4, and 5. Okay, so try those, and you can check your answer key in Final Sight or in the wherever I'm keeping them these days. Okay. All right, we'll see you back in the classroom.